Hey, everybody, welcome back. Um, I have nothing announcement or anything to do other than a reminder that Tuesday is the next exam that covering chapters 10 through 12. Okay. So if you have any questions, spend the weekend getting ready for it, I guess. And on Tuesday, we'll be here. I'll be here, I should say. If you have any questions, feel free to bring them in concerning those chapters. We can go over them. If not, we'll just continue with the chapters. Today is chapter 13. Again, a very short chapter, relatively short chapter. So if you don't have any questions, I will proceed. Okay. What we have here, this particular chapter is called Stoichiometry. Now, we've been doing this already. In balancing our equations, we came up with the coefficients that we, that we either, well, let me restate that. We've had general equations, 6 different types that we worked with. And then after we did whatever we're going to do to it as far as putting an equation out there, we went back and then we balanced it, and we could end up with something like maybe a 1-to-2 ratio between A and B. I did talk about the ratio between the reactants. This ratio is between the 2 reactants, and that is a 1-to-2 ratio. And remember, as a ratio, you can write it 1 or 2 ways, with either 2B in the numerator, 1A in the denominator, or vice versa. Okay. And then we talked about the ratio between the reactants and the products. So the relationship between, say, B and C, which is a 2-to-3, and the relationship between B and D, in this case is 2-to-1. And that is true also with A. We have a relationship between A and C and A and D, and we also have a relationship between the products in themselves. Okay, so we have a series of ratios that we can utilize to do calculations. So the last chapter, we introduced the mole. We talked about how to convert to the units of mole. Now, I stated then that this is important because I cannot relate A to B with respect to grams, that I need a factor, a common factor, which was the mole. And so now we're going to start doing examples of actual calculations of reactants, or calculate, well, if I start off with an X amount of A, let's say I start off with 10 grams of A, question may be, well, how many grams of B do I need? Well, from the grams of A, I first need to convert that to moles of A, because remember, the common factor is moles. And I need to know the molar mass of A. And so we went through that exercise on how to determine the molar mass of any compound. We add up all the atoms and how many of each there is, and look at the atomic weights and tally the whole thing up, and we end up with a molar mass. Okay, so from the molar mass of A and quantity of A, I now can calculate the grams of A. Okay, once I've done that, given the mole ratio, now I know that there's a mole ratio of 1-to-2 with respect to A and B. So if I have 10 A's, 10 moles of A, guess what? I need 20 moles of B, because that ratio is 1-to-2. Okay, and if I start off with, let's say, 10 moles of B, I only need 5 moles of A, because the ratio again is a 2-to-1. So that ratio is important, and that ratio came from the balanced chemical equation. So that's why it's important that we're going to end up being given a sentence of a reaction. From that sentence, we're going to create or generate the compounds. Okay, and knowing what's reacting, we can determine what type of reaction it is because we studied the six types of different reactions. And knowing that information, we can write the products. Okay. So you here see how we're putting it all together? We can write the products and then we can balance them. And then once we have that balanced chemical equation, now we can do any type of calculation relating reactants and reactants with products and so forth. And this is actually done even if you do it at a small scale, gram quantity scale in the lab. This is also true. This whole process with respect to calculations is true whether I'm doing it in the lab scale or I'm doing it in a big or giant industrial plant. Okay, so that's what stoichiometry is all about. It's that relationship between the ratios of the mole ratios of reactants. Okay, so let's take this example. We have a reaction of nitrogen monoxide reacting with oxygen to give us nitrogen dioxide. Okay, it looks like it's balanced. Let's check it out, make sure. And so we got 2 nitrogens in reactants, 2 in the products. We have a total of 4 oxygens on reactant side and 4 in the product side. Therefore, it is balanced. Okay, so what is that reaction? How do we interpret that reaction? Well, we can say that it takes 2 molecules of nitrogen monoxide for every 1 molecule of oxygen. You see that? It takes 2 of NO for every 1 of oxygen. And when that process occurs, we end up with 10, okay? And so in this ratio, so 2-to-1 ratio set up here, or a 2-to-2 between reactant and products, or 1-to-2 between oxygen and nitrogen dioxide. And so if we multiply everything by a factor of 5, okay, and I start off with 10 molecules of nitrogen monoxide, well, based on the ratio of 2-to-1, I require 5 molecules of oxygen. And see, that ratio is still maintained. A 2-to-1 is the same thing as saying 10/5, okay? That ratio is maintained. The magnitude is of the numerator and denominator has just changed proportionally, but it's still the same ratio. All right, and then what that tells me is that I would create 10 molecules of nitrogen dioxide. Okay, well, we don't really do any dealings with molecules individually because you see, I hope you by now how small these molecules are. So we deal with moles. And so we can say that 2 moles of nitrogen monoxide plus 1 mole of oxygen reacts to gives us 2 moles of nitrogen dioxide. So this is 2 times, remember, 6.02 times 10 to the 23rd molecules, and this is 6.02 times 10 to the 23rd molecules of oxygen, which gives us 2 times 6.02 times 10 to the 23rd molecules. You know, this is a 1 here, and this is a 2. Okay. And so we're not dealing with individual molecules, but if we did, that would be incorporating Avogadro's number. But in lieu of that, we're going to use the terms moles. And so let me clear this mess up. We interpret this reaction by saying that 2 moles of nitrogen monoxide require 1 mole. Remember, there's no number here, but it's understood to be a 1, just like mathematics. Require 1 mole of oxygen to give us 2 moles of nitrogen dioxide. Okay. The next equation, we have nitrogen plus hydrogen reacting to give us, we call this guy ammonia. Okay, ammonia. And so, as the case with the above example, that is interpreted as either one molecule to 3 molecules to 2 molecules. So obviously, as I stated, we generally are dealing with moles. So 1 mole of nitrogen requires 3 moles of hydrogen, which altogether, once the reaction proceeds, will give us 2 moles of ammonia, okay? And so if I were to just draw the structures of this, I would say this would be nitrogen, and then we have hydrogen, three molecules of hydrogen, okay? And then when all said, everything's done and when the reaction is done, we end up with 2 molecules of ammonia. Okay. All right, 2 molecules or 2 moles. We really are interchanging the term molecules versus when I want to demonstrate the process, I say molecules, but when we're doing reactions, we're dealing with a large quantity and therefore we're dealing with moles. Okay, so let's do this. Anyway, before I continue, coefficients, they give us the mole ratios in that balanced chemical equation, okay? So you can see it's very important that we balance it correctly. Otherwise, those coefficients would be incorrect, which then will result in incorrect calculations with respect to these equations, okay? Let's take this specific example. We have the reaction here. We have iron 3 oxide right here, reacting with carbon monoxide to give us iron and carbon dioxide, okay? And so let's double check, make sure everybody's balanced. We got 2 irons on the left side, 2 on the right side. We have a total of 3 carbons in the left side. We got 3 carbons on the right side. We have 6 oxygens on the reactant sides, and sure enough, we got 6 oxygens on the product sides in the form of carbon dioxide. And so this reaction is balanced. Now we go and look at the ratios, and I'm just going to look at the relationship between the 2 reactants. And so it is 1 mole of iron 3 oxide over 3 moles of carbon monoxide. Or I can invert it. You give me the carbon monoxide on top, iron 3 oxide on the bottom. The other relationship is between the iron and the carbon monoxide. Okay, so between the iron and the carbon monoxide, it's a 3-to-2 ratio. So that's what this ratio is. And I can invert it. So it would be 3 COs over 2 iron. Okay, and that's between that. Now, I can continue and go with the other relationships and actually create even more relationships, because each relationship has 2 ratios written in 1 or 2 ways, right? And so this is between the 2 reactants, right? This one right here. So this is number 1 relationship, and then we got a number 2 relationship that we just did. But also you have the relationship between the iron 3 oxide and iron, okay? That's number 3 relationship. And then the iron 3 oxide and carbon dioxide, and that's number 4 relationship. And then the carbon monoxide, let me go back to yellow. Yeah, I'll keep it there. Carbon monoxide and carbon dioxide, that's number 5 relationship. And of course, between the 2 products, and that's number 6 relationship. Okay, so there are 6 relationships here in this total chemical reaction. Each one has a ratio that you can write 1 or 2 ways. So each one has 2 ratios. So you get a total of 12 ratios. Ratios between reactants themselves, between reactants and products, and between products themselves. Okay, and we can write in 1 or 2 ways. Which one we utilize, just like we did in the conversion of units with, inches to centimeters or vice versa, cups to ounces, whatever. We set them up just like before. We do nothing different. What do we do? Step number one, we identify what we're looking for. The question says, how many moles of iron can be formed from 10.2 moles of carbon monoxide? All right, so the point is this. They're asking you how many moles of iron. So I go up here and I write down what I'm looking for in the equation. Can be formed from 10.2 moles of carbon monoxide. And so we got 10.2 moles of this. And so the only two species that we're concerned about is the relationship between carbon monoxide and iron. We don't care about iron 3 oxide. Don't worry about this guy. We don't worry about this guy, okay? Because the question is only asking between iron and carbon monoxide. So once I use that and I mark my equation, now I know what I'm looking for. I don't concern myself with the iron 3, nor do I concern myself with the carbon dioxide, okay? I note the ratio, it's a 3:2 ratio, because I definitely will need that bit of information. So I write down what I am given, like before, 10.2 moles of carbon dioxide, okay? Obviously, I need to get to iron, so guess what? My iron is on top, my carbon monoxide is in the bottom. Oh, I put down carbon dioxide. Carbon monoxide, I check my units, I'm canceling. My relationship is between iron and carbon monoxide, so it's 2 irons per 3 carbon monoxide, okay? Check my units, boom, I set it up properly. Now it's a matter of, and definitely I'm gonna get iron as my answer the way I set that up, okay? And so now let me clear up my mess here. Okay, that's just showing the stoichiometry. So here I got 10.2 moles of carbon monoxide. My relationship is a 2 to 3. Okay, my carbon monoxides cancel out. I leave me with units of iron, which is what the question asked for. And so my answer is 6.80 moles of iron. Okay. And so if I start off with 10.2 moles of carbon monoxide, I will create 6.80 moles of iron. Okay. We will have sufficient. It's understood if I start off with 10.2 moles of carbon monoxide, I'm going to have sufficient of iron 3 for this reaction to proceed. In fact, it would be in excess. Okay, this would be in excess. All right, and what do I mean by in excess? Okay, well, think about this for a second. Let's do this. All right. All right. Here's my crude drawing of a bicycle. Very crude drawing. Obviously, that's where the wheel is going to go. I got your seat, there's the handlebars. And obviously, this is my tires. And obviously, our stoichiometric relationship is a 1 to 2. Okay. And so to get my bicycles all together and assembled, I'm set up here. So if I start off with one frame and I have, 2 tires, obviously I'm going to make a 1 assembled bike, right? Oh, assembled bicycle, bike. Now, if I start off with 10 frames and I have the 30 tires, how many assembled bicycles would I have? Okay, I got 10 frames, 30 bicycle tires. How many assembled bikes would I have? Given the ratio that you can see. So 1 to 2. Anybody tell me that? Come on, I know you can. I got 10 frames, 30 bicycle tires, excuse me. How many bikes am I going to fully assemble? That would I have at the end when I'm done assembling them?
10.
Exactly. So let me draw this in different colors. So I will have 10 assembled bikes. I will have 0 frames, correct? And how many tires would I have left over?
20.
20?
Yeah.
Are you sure?
No. 10.
10, you got it. Okay. So in excess, this is an excess. The tires are in excess. And so what limits my process of making the number of tires and bicycles at the end is, in this case, the number of frames, because I have an excess number of tires, okay? And the difference can also be true if I reverse it. I can make up not enough tires, but an excess number of frames. That whoever's in excess is what we call, it is an excess, but what is not in excess is what we call the limiting factor, in our case for reactions, the limiting reagent. And that just means that that reagent will be used up first, and the other reagent that's part of the reactants will be in excess, okay? And so for the examples that we've been doing here, that we'll be doing is this. Iron 3 oxide will be in excess, okay? Because our only concern based on the equation was the relationship between carbon monoxide and the iron. Whoa. And the iron, okay? That's the only relationship. We don't care about the iron 3 oxide because it is in excess. Okay? I tell you that because sometimes, for some reason, iron 3 oxide is put into the equation and calculations, and it's not necessary. We're only concerned about what the question asked you for. Let's take another example. Here this says, how many moles of iron 3 oxide are needed to form 17 moles of carbon dioxide? And so let's go to our equation. We are dealing with iron 3 oxide and carbon dioxide. Okay. And we need to know how many moles of this, if we made 17 moles of carbon dioxide, how many moles of iron 3 oxide was utilized? And again, we're not concerned about the other guys, okay? Only between what the question asked. So we note the relationship. It is a 1 to 3 ratio, okay? As always, we write down what we're given, 17 moles of carbon dioxide that is given to us in the problem. We have our conversion factor, which comes from the balanced chemical equation. Since we're looking for iron 3 oxide, we can see that that has to be in the numerator, given the problem that we're asked. And carbon dioxide has to be in the denominator. And so it's a 1 to 3 relationship. Check out my units, make sure carbon dioxide cancels, leaving us with units of iron 3 oxide, which is what the question asked for. Okay, so here we go. And you should have a third of the iron 3 oxide is necessary because that ratio is a 1 to 3. So a third. So units cancel carbon dioxide, leaving me with units of iron 3 oxide, which is what the question asked for. We don't care about any other reactants or anything else, okay? Just what the question asks for. All right. All right, let's balance this equation. If we put 2 sulfur dioxides, 2 sulfur, we got one, let's restate that. Adding a 2 in front of sulfur dioxide and a 2 in front of sulfur trioxide gets us balanced here. Let's double check. We have 2 sulfurs on the left, 2 on the right. We're good with that. Sulfurs are okay. We have 4 oxygens over here. We got 2 oxygens over here. Total of 6. 6 oxygens total, meaning, and then so we check the products. Yep, we got 6 oxygens over here. Okay, so we're good with that. We are balanced. Okay. All right, so now questions asking you, how many moles of sulfur trioxide will form if you have 0.165 moles of oxygen? So they're talking about sulfur trioxide. How much of that is if we start off with 0.165? Okay. Now notice we're using small numbers here. Before we were doing whole, nice, big whole numbers, but that ratio, remember that ratio that we're using is the same, whether we're using nice, big, giant whole numbers, or we're using numbers much less than 1, okay? The stoichiometry does not change from the balanced chemical equation. It's still the same, all right? And we do this just like we've been doing any of these problems to date, is we write down what we are given. Okay, that's moles of oxygen. We know we have a conversion factor, and we're being asked for how many moles of sulfur trioxide. So that obviously has to go in the numerator, and oxygen must go in the denominator. Okay, so we got a 2-to-1 relationship. Check your units. Oxygens cancel. So we're going to require, what's going to require? We will make twice the amount of the sulfur dioxide, I should state. Let me clear my drawing. Now, note this. We are right now still dealing with just moles. The next logical step is to get into grams, because we're in the lab. We can't measure moles, okay? We don't have a balance that says, okay, we're going to measure that in moles. You can program it to do that, but we don't have that. We generally measure in grams in the lab scale. And in industrial park, we're talking about tons. But either way, tons or grams, that ratio is the same. And so eventually we're in moles right now, but the next logical step is to get into grams. And to get into grams, we need the molar mass, okay? Because the molar mass has units of grams per mole. So I'm just getting you prepared. All right, so in next question, how many moles of sulfur dioxide are needed to make 0.042 moles of sulfur trioxide? And so now we are talking about sulfur dioxide and sulfur trioxide, okay? And we need to learn to make, we need to know how much, we need to make 0.042 moles of this. So how much of sulfur dioxide we need to start off with? Notice our numbers are getting smaller. We're getting into the lab scale, but that ratio is still the same. So we write down what we're given for 2 moles sulfur trioxide. We have a conversion factor, obviously, because we're looking for sulfur dioxide in the numerator, sulfur trioxide in the denominator. Okay, we go to the balanced chemical equation. We got 2, it's a 2-to-2 ratio, and obviously it is a 1-to-1 because 2/2 gets canceled. But until you're comfortable with that, put the coefficient down, even though they're both the same number, until you're comfortable with realizing and recognizing you're dealing with a value of 1. Okay, and so it would take 0.042 moles of sulfur dioxide are needed to make the same amount of sulfur trioxide. All right, so up to this point, like I stated, we've been dealing with just the moles. So here's another flow chart for you, okay? And how this works, quite straightforward, I think. If you're given something in units, in grams, in units of grams, we need to get to moles. Remember, this whole calculation bit, we got to get to moles, okay? Well, if I need moles, guess what? If I start off with grams of some molecule, I need the molar mass. Because remember, the molar mass has units of grams per mole. So I need to go from grams to moles using the molar mass. Once I do that, I now have the moles given. That's what I'm given in the problem. From the balanced chemical equation, that mole ratio, now we can determine the moles that we're looking for, which is moles, fine, what we're looking for, what the question asks for. And once we write the correct chemical formula, which recall, we did that before. Remember, we have to write the formula first. And then once we write the formula, we can calculate the molar mass. Because again, molar mass is in units of grams per mole. And that puts us now into grams of A, or grams. I was thinking of giving an example here. But anyway, we'll have a specific example here in a bit. But that will give you the number of grams of whatever chemical you are trying to calculate. Okay. All right. So grams given using the molar mass gives you the moles given. Using the mole ratio gives you the number of moles of what you're looking for, which using the mole ratio of the compound you're looking for, then gives you the number of grams. It looks complicated, but it's not. We're going to end up with at least 3 conversion factors, okay? And the first one generally is the molar mass of what you're given, okay? The mole ratio is the middle one, and then the molar mass of what you are looking for, fine. So 3 conversion factors at the minimum, okay? And then utilizing your units, making sure you set it up properly to help you go across from point A to point B, and check through the units, you'll find you get to where you need to over here, grams. So X number of grams of some compound using these conversion factors will get you to number of grams of what you're looking for. Okay, let's take this example here. We have iron 2 oxide reacting with aluminum to give you iron, elemental iron, and aluminum oxide, okay? That is how you might read a sentence, okay? You might be given that like I just read it. Iron 2 oxide in the presence of aluminum, and we'll give you, oh, bear with me. Okay, I'm back, sorry. Okay, so like I stated, it might be written out. Iron 3 oxide in the presence reacts with aluminum to give you iron, elemental iron, and aluminum oxide. You have to take the words and break it down to the chemical equations. We've done that exercise before. Then once we do that, we balance it, which we also done that exercise. okay, which this definitely looks like a single replacement reaction, right? The aluminum is replacing the iron in the iron 2 oxide, okay? So we balance it, and then we note the ratios of what we're looking for. Okay, note the ratios of the reaction, 3 to 2 for iron 2 oxide and aluminum, and so forth. Okay. Now, next question they might ask you is this. All right, calculate the mass of iron 2 oxide needed to react completely with 5.55 grams of aluminum. And so we're only concerned, and that's again, I overemphasize this, we're only concerned about the reactants. Okay. So if you start off with 5.5 grams of aluminum, how many grams of iron 2 oxide you need is essentially a question. Okay, is what they're asking you. Okay. This could be a two-part question here. And then a second question could be, change the color here, calculate the mass of aluminum oxide. Aluminum oxide, so we're talking about one of the products produced when 10.25 grams of aluminum reacts. So that's our relationship that we're concerned about for the second equation, second problem. Okay. So I can't overemphasize that when it comes to that question, you only need to worry about what the question, the reactants and products of what the question asked you. Okay. All right, so we got two different questions, two different types of calculations. I shouldn't say different types, it's just one relates with the reactants, and one relates with one of the reactants and one of the products, okay? That's what I mean by different types. You're going to do this in very similar manner with respect to the mathematics involved. All right, let's take the first one. We still got the equation there. We start off with 5.55 grams of aluminum, okay? Well, obviously, the first thing we need to do is to convert that to moles. We cannot do grams to grams. We got to go to moles. So what do we need? Here, okay, our relationship is between the iron 2 oxide and aluminum. Okay, we don't care about anything else. And so we need the first conversion factor converts us to moles of aluminum. This is the atomic weight, 26.98. Oh, change color here again. Yeah. Grams of aluminum cancel grams of aluminum, okay? So the first one is the atomic weight. And now the second one, we need to get into iron 2 oxide moles. And we do that from the stoichiometric relationship between the iron 2 oxide and the aluminum, and that comes from the balanced chemical equation, okay? As we proceed here, keep track of your units. Notice here that we have set it up properly, and our units that we started off with are being removed and get into the units that we're looking for. The question asks you to figure out how many grams of iron 3 oxide are necessary. At this point, you are only at moles of iron 3 oxide, so obviously what do you need? You need, in this case, the molar mass of iron 3 oxide. So you look at the atomic weight of iron, atomic weight of oxygen, add them up, and it should add up to 71.85 grams per mole. Okay. Now you continue to check your units, and at this point, you are in the units that the question asked for, and that is how many grams of iron 3 oxide that represents. And so now that is 22.2 grams, okay? So what this is telling you is this, that if you start off with 5 0.55 grams of aluminum, I need at the minimum, for all reactants to react completely, is 22.2 grams of iron 2 oxide. If I have more, then I'm going to have excess iron 2 oxide. If I have less, I'm going to have excess aluminum. Okay, but I need to have that amount of each, so they all react completely and they give us all the product that we're looking for. Okay. Next one, we're dealing with 10.25 grams. So our relationship here is between the aluminum and the aluminum oxide. That's all we care about. Don't care about the other things. Okay. So as we did in the first example, we needed to convert aluminum to moles of aluminum. Okay. So as we did number one, we needed the atomic weight, of aluminum, which is 26.98. You obtain that from the periodic table. Okay. Check your units. We are in moles of units at this point in time if we stop the calculation. But we're not going to stop it because we need to get to aluminum oxide. So now the next conversion factor is the mole ratio, the stoichiometry between the aluminum oxide and aluminum, which is a 1:2 ratio. And that comes from the balanced chemical equation. Okay, I can't overemphasize that balanced chemical equation. You can see here, if it wasn't balanced, that 2 could be a 1, and right away your numbers are not correct. Okay. And then finally, as I progress, the last conversion factor will get me into grams of aluminum oxide. Okay, grams of aluminum oxide, and we need the molar mass of aluminum oxide, which means I got, add up 3 oxygens, 2 aluminums, that adds up to 101.96 grams. Okay. And then plug it in there, and we end up with 19.37 grams. So if I start off with 10.25 grams of aluminum, and obviously I'm going to have the iron 3 oxides, a sufficient amount, I should create 19.37 grams of aluminum oxide. Okay. And this relationship, this ratio, this calculation is true whether we started off with 10.25 grams of aluminum or 10.25 tons of aluminum. Okay. Well, I should metric tons, because these units are in metric units. And we will end up making 19.37 metric tons of aluminum oxide, which is an abrasive material. You find that a lot in sandpaper, aluminum oxide. All right. Let me clear my table here. So we gave you a flow chart before, which dealt with the STP conditions, and that's written in yellow, that relationship of 22.4. Now we got a flow chart here that will help you with any type of these problems. Okay. Now, the thing is to remember, we need to get into moles all the time. We can't go directly from grams given to grams fine. We can't do that. That's not, we have to go, if we're looking like this exercise, what we just did, it went from grams given all the way to grams, what we're looking for. Okay. And we need the molar mass of what's given. And we need the mole ratio from the reaction, balanced chemical reaction. And then we need the molar mass from the product. Okay. And that is what we did with this previous example. Also remember that if we are at STP only, okay, we can go into volume. If we're given grams of some material, and we got obviously its molar mass, and that gives us the moles given, and then the balanced chemical equation converts us to what we're looking for, moles given. we have two choices here. We can go down, bottom right, if we are at STP, to figure out the volume of the gas that we created. Or we can go up with the molar mass to give us the number of grams, okay? So we can go from the top left to the bottom right. Keep in mind, I'm going forward direction, but you can go in the backward direction too. If you're given an X amount volume of gas at STP, you can calculate backwards to figure out grams of some material, okay? This is all this flow chart, these blocks, you can go in both directions. But this particular flow chart is very good, very helpful when you're going through these stoichiometry calculations. Okay. Here's an example of a problem that is written out, okay, in words, and you need to convert it to an equation followed by balancing it out. And then we're going to do some calculations. So here it is what it says. Write and balance the reaction of hydrochloric acid and solid cobalt. Let me change the color here. Yeah, let's do that one. All right, so write and balance the equation of hydrochloric acid and solid cobalt. Now, cobalt is not one of the sweet 16 metals, okay? So you need to be given the information as far as this oxidation state. And so that's what they're telling you right here. Cobalt will be in the +2 state. So it will be in the +2 state in this reaction, okay? So here we go. We have cobalt, solid, reacting with HCl aqueous. Okay, this is a classic example of the metals I was explaining to you when we dealt with the activity series. This is a single replacement reaction. Okay, remember that the metals that were highlighted in activity series were bright color, they reacted with metal quickly, but the metals between that batch and hydrogen, you needed hydrochloric acid. And one of the products you always received was H2 gas, okay? And then you create your substitution reaction. So cobalt goes to cobalt 2, given the information up here. And then you got chloride, so you got chloride over here, okay? And so we first, like I explained before, write the ions and they determine the correct ratio to put them in. And this tells us that we need 2 chlorides for every cobalt, okay? So now we can write the formula for cobalt 2 chloride. And if you look at the solubility rules, you'll see that cobalt chloride is soluble, so hence we can put AQ, okay? Balance it. Well, if we put a 2 in front of HCl, that balances the hydrogens, and that kicks up my chlorides, but I needed 2 chlorides, so by default, the cobalt 2 chloride chlorides are balanced. And then I only need 1 cobalt, so everybody's happy, okay? I got the physical states here. I'm good to go. All right, so now let me clear it up a little bit. We write the reaction, which is what we just did, okay? All right, so now we have a balanced chemical equation. We started off with a equation that was given to us in words. We took those words and converted it into a balanced chemical equation. We also recognize that this is a single replacement reaction. Excuse me, single replacement reaction. Okay, and that one of the products is H2 or gas, hydrogen gas, because those are the ones, the metals between the both. I don't have my periodic table on, but those are the metals that react with that before hydrogen, but after sodium that require more acidic conditions for them to react. And all of those produce hydrogen. And then the corresponding chloride. All right. I can't overemphasize too, for the ionic compounds, I put them into ion form first before I put them together. That way I'm assured that I put them together in the right ratio. So here's the question. Okay, so how many liters of gas at STP will form if 5 grams of cobalt react? Okay, and it's kind of tricky if you think about it. It shouldn't be, but they're saying gas, right? How many liters of gas? Well, you know the products. One's aqueous, is soluble. The only gas, obviously, is hydrogen. And so the question is, how many liters of hydrogen gas are generated if I react 5 grams of, cobalt? So we are only concerned about cobalt and hydrogen gas in this equation. Okay, so we write down what we're given, right? We're given 5.0 grams of cobalt. Obviously, oh, hold on, I forgot to emphasize another point. STP, okay? That should indicate to you that I may not need it, but I have available to me 22.4 liters per 1 mole. Okay, because I'm at STP. But guess what? I might need it. All right, so write down what you're given, 5 grams, 5.00 grams of cobalt. Okay, I need to determine the moles. I got to convert to moles. I need the atomic weight of cobalt. Look it up, you'll see it's 58.93. Notice that my grams cancel, grams of cobalt cancel. Okay. Next is the stoichiometric relationship between hydrogen and cobalt. Okay, that's how I can get into moles of hydrogen. Okay, because from the balancing chemical equation, it's simply a 1-to-1 relationship. Okay, but I put these up here because I want to follow my units and I want to make sure I've got this set up properly. Now, the fact that we are in STP at this point, if they did not mention STP, I could not calculate the liters. The best I can do is calculate grams. Okay, but they told you are STP, therefore I can utilize the final relationship, which is the 22.4 liters per mole. Okay, because we are at STP. And so our units continue to cancel properly, leaving me with units of liters, which is what the question asked. And so now it's a matter of, hold on, let me clear this up. Plug it in the numbers and figure it out. Calculate. So if you start off with 5 grams of cobalt and you happen to be at 0 degrees Celsius, which is STP temperature, okay, and 1 atmosphere, I will create almost 2 liters of hydrogen gas, well, 1.90 liters of hydrogen gas, okay? Note, I got 3 conversion factors here. This is grams given, moles given, the mole ratio to get me to find. This gives me the volume of volume find, okay? Because I'm at STP. All right. Now, if 2.374 liters of hydrogen gas is formed, okay, how many grams of hydrochloric acid reacted? Okay, now we're just concerned about hydrogen gas and hydrochloric acid, which, you know, is a 2-to-1 relationship. And so if they ran the reaction and they were able to measure the volume of hydrogen gas, they determined that it was 2.374 liters of hydrogen gas. Now they want to know, well, okay, well, how many grams that were required to create that much hydrogen gas? So we're only concerned about hydrogen gas and hydrochloric acid. Okay, so again, write down what we're given, 2.374 liters of hydrogen gas. Okay, we are still at STP, so I got to convert my, if I'm in grams or liters volume, I got to get to moles. So that one gets me into moles of hydrogen gas. Then I look at the stoichiometric relationship between HCl and hydrogen gas, and it is a 2-to-1 based on the balanced chemical equation. So at this point, keeping track of my units, you can see my liters cancel, my moles of gas cancel, leaving me with moles of hydrochloric acid, but they're looking for grams. So obviously I need the molar mass of hydrochloric acid. Okay, it's 35.45, I believe. Yep, for chlorine, and then 1.01 for hydrogen gas. That's a total molar mass of 36.46 grams HCl. Okay, check my units. I know I sound redundant, and I do that for a reason, because I've seen a lot of variations, and it's been, these type of equations have been made very complicated by adding 6, 7 conversion factors, and I'm trying to tell you, you don't need to do that. Okay, just keep track of. That's why I mark up the balanced chemical equation, and so I'm only concerned about what I marked up. Okay, that's my relationship. Nothing else matters with any other reactants in this reaction. Okay, so at this time I plug it in, and I end up with 7.72 grams. Now notice the sig figs. We haven't forgiven sig figs. Remember the 22.4 liter, that's a measurement, so it can be a factor with respect to sig figs. Okay, the mole ratios, those are whole numbers, do not play a factor. The atomic weights, I've explained that atomic weights, molar masses, they come from whole numbers. No, they're not a factor. And so the only thing that's a factor here is either the 22.4 or the 5.00 grams, because both of them are measurements. So they got 3 sig figs for the grams, 3 for the 22.4. So our answer has 3 sig figs. Okay. Same scenario here. The mole ratio is not a factor. The atomic weights are not a factor, but the 22.2 could be a factor. You started off with 4 sig figs, 22.4 has 3 sig figs, so your answer should have no more than 3 sig figs. Okay. All right. Let me clear my mess. Right. Hydrochloric acid plus oxygen gas produces chlorine gas and water vapor. Interesting. Okay. All right. So let's write down what they're telling you. HCl gas plus oxygen gas, keyword oxygen gas is diatomic, okay, produces, which is the arrow, chlorine gas, again, diatomic, plus water, which is H2O, but then they add vapor. Okay, so that means that note everything here is in gas phase. Okay, it is in gas phase. Now the question says, how many liters of chlorine gas? Oh, let's double check. Are we balanced? Almost forgot. Okay, I got 2 chlorines on the right. If I put a 2 on the right, it gives me 2 balances my chlorines. Okay, it balances my hydrogens, but my oxygens are not too good. And so what suggestions, what can I do? I'm not balanced here. Anybody have any ideas? Any ideas on how to balance this guy? No ideas? Well, I guess we can go on. All right, let's try this. All right, we got 2. Let's go back to where we were. I got 2 here, 2 chlorides, 2 CLs. Let's try doing this. All right, we try that. But so the chlorine or CLs are balanced, but we got 2 hydrogens. All right, now we got 2 hydrogens. Our oxygens are not up to par, but what happens if I click a 2 here? It balances my oxygens, but then that kicks up my hydrogens to 4. All right, let's move that 2 to a 4. And guess what happens there? My chlorides become 4. And what if I put a 2 here? Maybe that might work. Let's check it out. I got 4 hydrogens, 4 hydrogens, 4 chlorides, 4 chlorides, 2 oxygens, 2 oxygens. Looks good. Okay. Looks balanced. All right, let me clear my mess and we'll put the one up that looks a little better. All right, looks like we're balanced. Okay, so now the question says, how many liters of chlorine can be formed if we have 3 liters of oxygen react completely at STP? We're at STP, so we can keep this in mind. Okay, so we want to know about chlorine and O2. That's it. Okay. So let's write down what we're given. We have 3.00 liters of oxygen. Okay. Obviously, as I stated, we're going to convert that to moles. Okay. And then from the balanced chemical equation, we have a 2-to-1 ratio. It puts us into moles of chlorine, which then now we can convert back to volume. It's asking the question, how many liters? All right. And so that's the 22.4. And so what happens is now it's 6 liters of chlorine. So if you start off with 3 liters of oxygen, you will create 6 liters of chlorine. Now, do you see something interesting with respect to our conversion factors here? Could we simplify that a little bit more? Any ideas? Look at our conversion factors here. Is there something there here that we can simplify? Yeah, do not the 22.4, don't they just cancel each other out? Yeah, they do, okay? And so something to look at when you are looking at the reaction, and everybody's STP, and everybody's in gas phase, guess what? You can just simply just use the stoichiometric relationship between the two, whatever ones you're looking, either two reactants or the products or whatever, and just use that to get you to what you're looking for in volume, obviously. Obviously, if you got to convert to grams, you couldn't do that, okay? You'll have to stay in moles and then molar mass and so forth. But if you are dealing with gases all the way around and you're at STP, I can just simply just use the stoichiometric relationship between the reactants or reactants and products and so forth. Because the 22.4 liters cancels out both. Okay, hopefully you'll see that. All right, so try this at home. Okay, you got 15 grams. Here's the problem. Carbon reacts with oxygen gas to form carbon monoxide. Okay, that's the equation. How many liters of carbon monoxide at STP can be made from if you start off with 15 grams of carbon, okay? And then try it with the second part. If you start off with 20 liters of oxygen gas, you should get, for the first one, 28.0 liters of carbon monoxide and 40.0 liters of carbon monoxide. Okay, so try that at home. I know I gave you the answer there, but try to do it on your own. Let me summarize, because today what we have been doing, okay, little by little, we talked about the elements, we talked about the periodic table, we talked about how, with respect to ionic compounds and specifically the elements of the A metals, how they form specific ions, either cations or anions, and we put them together in the correct number of ratios so that the charges balance out. And a lot of times it's a simple 1-to-1, sometimes it's 2-to-3, sometimes 1-to-3, depending. But we added enough of each so they cancel out to make ionic compounds. Okay, we talked about writing covalent compounds. So from the elements, we created compounds. Once we had the compounds, we started reacting them with each other, making reactions, specifically 6 types of different reactions, okay? We learned about those reactions, and then we also learned about how to balance these reactions. And in those 6 types, I described the different steps that you need. Some of them had specific steps that you can do to balance them. Others, it was mostly a trial and error, playing with the numbers until things balanced out. So you try one number in reactant side, and that changes things in the product side, or vice versa, until such time that you have all the elements in the reaction balance each other out, okay? And so then from the balanced chemical reactions, that represented what we have called the stoichiometry ratios. What is the relationship between the reactants? It could be a 1-to-1, 2-to-1, 3-to-1, or reactants and products and so forth, okay? You created these ratios. Once we know that, we learned that, we did some examples of calculation reactants or products based on these ratios. And we calculated them in terms of either moles, grams, or volume if you are at STP, okay? And so you see how it's just extending here. And so this flow chart will help you. You follow the flow chart. As with anything, I advocate doing a systematic approach of solving the problem, one step at a time, until such time that you're comfortable, and then you can bypass it or combine a lot of steps, okay? But before you get that, follow these. You know, there's a lot of we have worksheets Don't forget the worksheets, work them through. Don't forget the sessions that Dr. Kim offers, okay? So, congratulations, you are done with chapter 13. All we got left is 14 and 15. All right, I guess most of the people are leaving.